welcome to my terminology video. I hope everyone has already watched my introductory video. If you haven't, I recommend that you do so in order to get an idea of my approach and a basic understanding of how we're going to proceed throughout this entire course. Today we're going to familiarize ourselves with some basic terms that I will use repeatedly in the rest of the tutorials. Most of the terms that I use are widely accepted in the world of Sudoku, but there may be a few deviations. So before I begin the actual lessons, I just want to make sure that we're all on the same page and that you will always understand what I am referring to whenever I talk about any of the following things. Okay, let's go over to the puzzle board. Okay, here we have our basic 9x9 Sudoku grid. This is called the grid. And the grid is divided into several subsections. As you can see, it has 9 horizontal rows. This is a row. And it has 9 vertical columns. And this is a column. And it has 9 of these large squares that we will call blocks. And we will call them blocks instead of boxes because we don't want to confuse them with these little boxes that we will call cells. So these are cells, and these are blocks. And as you can see, there are 9 cells in each block. And we will number the rows, columns, and blocks so that we can refer to them and any specific cells within them with precision. Some people use letters A, B, C, D, E, F, G, H, I for the rows, and then the numbers 1 through 9 for the columns. But we will use numbers for both. So this is row 1, this is row 5, and this is row 8, for instance. And this is column 2, and this is column 4, and this is column 9, for instance. And the blocks will be numbered like this. So this is block 1, and this is block 3, and this is block 7. You get the idea. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now when we want to refer to a specific cell, we will refer to the row number and the column number. For instance, this cell would be called row 4, column 3, or R4C3. The designation R4C3 are called the coordinates of this cell. And likewise, this cell would be called row 8, column 7, or R8C7, and so on and so forth. Every row, column, and block each contain exactly 9 cells. And further, each row, column, and block is also called a house, because each one houses all the numbers 1 through 9. So there are 9 rows, 9 columns, and 9 blocks, which means there are 27 houses, because each row, column, and block constitutes a house. 3 times 9 is 27. When the puzzle is solved, each of the 27 houses will all have the numbers or digits 1 through 9, with no repeats and no number or digit left out. And some of these houses intersect with each other. For instance, row 3 intersects with block 2. And the intersection of row 3 and block 2 would be these 3 cells. These 3 cells are in row 3 and they are also in block 2. This is what we mean by an intersection, or an overlapping. Row 3 and block 2 overlap to form this intersection. There is one more subdivision to describe, and that is a chute, spelled C-H-U-T-E, like a laundry chute. A chute is 3 blocks in a row, either horizontal or vertical. This is a chute, and this is another chute. Some people call these things bands, but we will call them chutes. And some people call the horizontal chutes floors and the vertical chutes towers, but we will simply call them horizontal chutes and vertical chutes. Please note that a chute is not a house. Only rows, columns, and blocks are houses. A chute contains 27 cells, as you can see, whereas a house only contains 9 cells. When I am referring to a particular number in the puzzle, I will use the word digit. Like I'll say digit 7 or digit 5, and sometimes this can mean just one of the digit 7s or it can mean all of the digit 7s, and you will know which based on the context. When you are presented with a new Sudoku puzzle, there will be some numbers already filled in to give you something to start with, like this. These numbers are called givens. They give them to you. And generally speaking, the more givens, the easier the puzzle will be, and likewise, the fewer givens, the more difficult the puzzle will be. But this is not always 100% true. You will usually see anywhere from, say, 18 to 35 givens. In order to be considered valid, each Sudoku puzzle must have only one unique solution. If there are multiple solutions, then the puzzle is not valid. And as you will see later, we can sometimes use the fact that there is only one unique solution to help us solve the puzzle. Most published puzzles have only one unique solution and are therefore valid. When we enter a digit into the puzzle as the solution to a particular cell, we will call that the cell's value. Like the value of this cell is 9, and this cell's value is 5, etc. In all the unfilled cells, the remaining digits that are possible values for that cell are called candidates. These little numbers are candidates, meaning possibilities. Some people call them pencil marks, which comes from the old-fashioned method of doing the puzzles with pencil and paper, but we'll call them candidates, like candidate 3 or candidate 6. Okay, now let's talk about what we mean when we use the term seeing each other. Like two cells can see each other, or two candidates see each other, etc. In order for a cell to see another cell, or for a candidate to see another candidate, they must both be in the same house. This is the only way. Being in the same house connects them in various ways. For instance, these two cells see each other because they are in the same row. And these two cells see each other because they are in the same row. And these two cells see each other because they are in the same column. And these two cells also see each other because they are in the same column, column 9. And these two cells see each other because they are in the same block. And these two cells see each other because they are also in the same block. But be careful. Notice that these two cells, even though they are touching at the corners, do not see each other. This cell is in row 4, column 3, and block 4. And this cell is in row 3, column 4, and block 2. They do not have any house in common. And don't confuse this with a third cell that can see each of two other cells, even though those two other cells do not see each other, like this. These two cells do not see each other. Yet, this cell can see both of them. It sees this cell because it's in the same column, and it sees this cell because it's in the same row. And here is another interesting example of the same thing. This cell and this cell do not see each other. Yet this cell sees both of them because it is in the same column with this cell, but it's in the same block with this cell. So they do see each other. Even though it looks like they're out of line, They see each other because they are within this house, this block. So this cell, the yellow one, sees both the blue ones, but the blue ones do not see each other. This concept is very important and will come into play over and over again in a multitude of the solving techniques I will show you. Also, please note that any two cells that see each other cannot have the same value. Two cells that see each other cannot have the same value. That's a law. If they see each other, they must be in the same house, and we know that any particular digit can only occur one time in any given house, according to the basic rules of Sudoku. Okay, now let's talk about strong links and weak links. The next video, video number 3, will describe these two very important things in great detail. But for now, let's just learn the simple definition of each one. A strong link can occur in two ways. First, when there are exactly two instances of a particular candidate in a house. So let's take a look at that. Here we see candidate 1 spread out through this puzzle. Now in the top row, we see that there are only two instances of candidate 1, so there is a strong link between those two ones. And there are only two ones in column 9, so there's a strong link between those. Over here, let's see, in block 1, there are only two ones within this house, block 1. So there's a strong link between those two ones. And there are only two ones in column 2. So there's a strong link there. There are several all over the place. Here's another one. There's a strong link between these two. They're the only two ones in row 5. Okay, another way that there could be a strong link is when there are only two candidates remaining in a cell. Like, for instance, this 6 and this 9 are strongly linked because they're the only two candidates in that cell. This cell has to be solved with either a 6 or a 9. It's one or the other. So that's a strong link. Here's another one, the 8 and the 6. There's a strong link between that 8 and that 6 within the cell. Here's another one. There's a 3 and a 6. There's a strong link between this 3 and that 6. And here's another one. There's a strong link between this 8 and this 9 because they are the only two candidates in that cell. So a strong link occurs when there is only two possibilities for either two different candidates within a cell, or two of the same candidates within a house, like we showed before with the ones. And a weak link occurs when there are 3 or more instances of a particular candidate in a house. Like, we'll go back to these ones again. There are 3 ones in this house, in this block. So there can only be a weak link between any two of them. So between these two, there's a weak link. Between those two, there's a weak link. And between those two, there's a weak link. Now in this row, 7, there are 4 ones. So there can only be a weak link, not a strong link, between any two of them. Between these two outside ones, or between the two inside ones, or between this one and that one. Because there are 4 ones in row 7, there cannot be a strong link. Any two of those can only be weakly linked. Okay, so in column 5, there are 4 ones, so there's only a weak link between any two of those. And in row 2, there are 3 ones, so there's only a weak link between these two, or between those two. There's only a weak link. And now we'll go to the other diagram, and we will see that within this cell, for instance, there are 3 candidates in this cell, so there can only be a weak link between the 3 and the 9, or between the 3 and the 6, or between the 6 and the 9. There can only be a weak link. And anything 3 or greater, so let's take a look at one, like there's 5 candidates here. So between the 7 and the 3 is only a weak link. Between the 7 and the 5 is only a weak link. Between the 5 and the 9 is only a weak link. So between any two of those 5 candidates within that cell, there can only be, at best, a weak link. And give another example. Here, there are 4 3s in this row, in row 5, so there can only be a weak link between any two of those 3s. And within a cell, for instance, down here, between the 8 and the 3, there could only be a weak link because there are 5 candidates in that cell. The only time there can be a strong link is if there are 2 candidates, 2 within a cell of different digits, or 2 in a house of the same candidate, here being 1. And also, in order for there to be a link, weak or strong, between any 2 candidates, they must see each other. In other words, the 2 candidates must be in the same house. Like, there cannot be a link between these 2 ones because they don't see each other. To sum this section up, in order for there to be a link, weak or strong, between 2 instances of the same candidate, they must both be in the same house. And in order for there to be a link, weak or strong, between 2 different digit candidates, they must both be in the same cell. And any link, weak or strong, is only between 2 candidates. Now we will cover strong links and weak links more thoroughly in the next video, video number 3, where we will learn their formal definitions and their implications. But for now, I just want you to familiarize yourself with these terms. Okay, let's move on. Next, we have what's called a bi-value cell. This is a cell with only 2 candidates remaining in it, like these. These are all bi-value cells. Bi meaning 2, just like a bicycle has 2 wheels. A bi-value cell has 2 candidates. When you have a lot of bi-value cells left in a puzzle, there are lots of ways you can use them to crack the puzzle wide open. You want to see a lot of bi-value cells. They are really powerful assets. They are your friends. And notice that there is a strong link between the 2 candidates in any bi-value cell. We know that one of them must be true and the other must be false, even though we may not know which at first look. For instance, between this 5 and the 9, they're the only 2 remaining possibilities for this cell. So it either has to be a 5 or a 9, and so that's a strong link. When you have a strong link between 2 candidates of the same digit within a house, like we had with the 1s, they are called a conjugate pair. These 2 ones are called a conjugate pair. The strong link refers to the link between them, but the term conjugate pair refers to the candidates themselves. This is a subtle distinction, but I think it's important to note. As I mentioned earlier, there is also a strong link between the 2 candidates and a bi-value cell, between these 2, between those 2. But it is not customary to call these 2 digits a conjugate pair. I guess because it's 2 different numbers, 2 different digits. Okay, let's talk about subsets. A subset in Sudoku is defined as n number of candidates in n number of cells, with n being any number between 2 and 9. In other words, 2 candidates in 2 cells, or 3 candidates in 3 cells, or 4 candidates in 4 cells, and so on and so forth. And don't forget that in order to qualify as a subset, all the cells and all the candidates of the subset must be contained entirely within at least one house, like a row, a column, or a block. Note that you cannot have a subset of a single digit. If you have a single digit as a candidate, then that is the value for that cell, case closed. Subsets appear in 3 different ways: naked, hidden, and locked. However, only subsets of 2 candidates or 3 candidates can be locked. I'll explain why in a minute. Well, first, let's take a look at some naked subsets. Subsets of 2 candidates are called pairs. And subsets of 3 candidates are called triplets or triples. And subsets of 4 candidates are called quadruplets or quads. And subsets of 5 candidates are called quintuplets or quints. And subsets of 6 candidates are called sextuplets, but I just call them sixers. Subsets of 7, 8, or 9 are not going to help you very much, so I don't go out of my way to look for them. In a house with no givens, A subset of 7 might jump out at you, and if it does, then use it. Just know that they don't come up very often. But subsets of 2, 3, 4, 5, and 6 do come up often, and you better be able to spot them. Pairs and triples are not very difficult to find. But at a bare minimum, you must be able to spot quads, and if you can spot quints, you'll be in good shape. But if you want to be a real expert solver, you'll need to be able to spot sixers too. A naked subset is one in which the subset candidates are the only candidates in the particular cells. Here are some examples. These are pairs. This 7 and 6 and 7 and 6, they're the only two candidates in these two cells. Now be aware that there are other candidates and values in these other cells in row number 1 here, but we're just looking at these two right now. And if you see something like this, we know that one of these must be a 7 and one must be a 6. Likewise, in this column, one of these must be an 8 and one must be a 9. And over here in this block, one of these cells has to be a 4 and the other one has to be a 2. We don't know which, but that is a pair. That's a subset called a pair. In the next example, we're going to have triples. And here we have 2, 6, 9, 2, 6, 9, 2, 6, 9, 3 cells with 3 candidates. That is a triple. That's a subset of 3. But be aware that in subsets that have a greater number of candidates than just 2, say 3, 4, 5, 6, 7, 8, and 9, all the candidates do not need to be in all the cells. For instance, here we have a triple of 5, 8, and 3, but here only the 5 and the 3 are here, only the 5 and the 8 are here, and only the 8 and the 3 are here, but there's still 3 candidates in 3 cells. And later we'll find out that that means these 3 cells have to contain those 3 digits, but we'll worry about that later. Over here we have another triple of 1, 4, and 7, and it's within this house. It's within this block, block number 7, 1, 4, 7, 1, 4, 7, and only 4, 7 here, but this still constitutes a triple. Okay, a hidden subset is one that is there, but it's camouflaged by the presence of other candidates. So before we saw that there was a 7 and a 6 in these two green squares, green cells rather. And now if you look carefully, there is no 7 or no 6 outside of these two colored squares. So that pair of 7 and 6 and 7 and 6 is still in there, but it's hidden by the 5 here and by the 1 and the 2 here. So when you look at this row, you need to be able to say to yourself, wow, look at, in these two cells, there's only these two candidates, a 7 and a 6 and a 7 and a 6, and they don't occur anywhere else. And let me tell you what, it's not that easy to see. Because without the coloring, it's not as easy. But when you get to be an expert Sudoku solver, you will look at that top row and you will identify that there is a hidden pair in there. That's what that's called. The 7 and the 6 are a hidden pair. And likewise with a triple, we're going to look at this column. I'm not going to give examples. Everything would take too long. So here we have that same triple that we saw earlier as a naked triple. It's still in here. 5, 3, and 8. 5, 3, and 8. Here's 5, 3, 5, 8, and 3, 8. That's a triple, and that's in there. And those 5 and the 3 and the 8 do not appear anywhere else in this column except in those 3 cells. And so that still constitutes a subset of a triple within those 3 yellow cells. But it's hidden by the presence of those extraneous candidates. A locked subset is one that is contained within 2 houses at the same time. It lies in the intersection of 2 houses, either within a row in a block or within a column in a block. Let's take a look at some examples. Here we have a 7 and a 6 and a 7 and a 6. 2 candidates in 2 cells. So that is a naked pair. But not only does it lie in row 1, it also lies in block 1. So we call that a locked pair. Likewise, the 3 and the 9, the 3 and the 9, a naked pair, lies in row 3 and block 2. So that is a locked pair. And here we have a naked pair of a 4 and a 5 and a 4 and a 5, but because they lie in column 1 and block 4, we call it a locked pair. Now notice down here, this 8 and 9, 8 and 9, this is a naked pair, and it lies in row 9. But this naked pair does not share the same block, so it cannot be a locked pair. It's a naked pair. And up here we have 1 and 2, 1 and 2. This is a naked pair that lies within block 6. But because they don't lie in the same row or the same column, they're only a naked pair and not a locked pair. So now let's look at the triples. Here we have 2, 6, 9, 2, 6, and 2, 9. 3 candidates in 3 cells, and they lie in row 2 and block 2. So this is a locked triple. They lie in 2 houses at the same time. And here's another intersection of column 2 and block 4. We have 4, 7, 8, 4, 7, 8, 4, 8. 3 candidates, 3 cells. That's a naked triple, but because it lies in 2 houses, the column and the block, we call it a locked triple. Now down here, this is not a locked triple. We have 3 candidates and 3 cells, so it's a naked triple, but it only lies in row 8, and they don't share the same block. Now, if this 5, 6, and 9 were moved over and was in this block, it would be a locked triple, but it's not. Now, some people call any naked subset a locked subset, which is okay, but technically it is only locked if it lies in 2 houses at the same time, as I just showed you. Now let's see why a locked subset, according to this definition, can only be 2 or 3. Let's try to do it with 4. It can't be, because in order to be in 2 houses at the same time, there's not enough room to put all 4 candidates. Like here we have 2, 3, 5, and 8. That's a naked quad. But this cell is outside of the block, so you can't get 4 candidates in those 3 cells and still have it be a quad. So you cannot have anything higher than a 3 as a locked subset. So locked subsets can be of 2 candidates or of 3 candidates. Okay, the last thing we'll talk about today will be alternate inference chains, or AICs as they're called. I will describe these more fully in video number 4, and then later on in the course there'll be about 7 videos dedicated to all the different types of these, and I'll go into great detail on them. But for now, just know that an AIC is a series of connected links alternating between strong and weak that form a chain from which inferences can be made and conclusions can be drawn about the remaining candidates in a puzzle. Okay, that's all the terms for today. Let's go back outside and finish up. This comprises the lion's share of the terms I will use. These are the basic ones. There will be several more that we'll come across and learn as we discuss each solving technique, but for now, if you're with me on what we've discussed today, we're good to go. Okay, that's it. Thanks for watching, and I'll see you in the strong links versus weak links video. Until then, be well and be happy.